Number one, what is electromagnetic induction? So electromagnetic induction, it's a fancy word for when changing a magnetic field through a loop of wire induces a voltage. So when you change a magnetic field through a loop of wire, it induces a voltage. That's called electromagnetic induction. And electromagnetic induction is something that happens all the time. Did anyone leave glasses back here? There's just a pair of glasses back here by the sink. That seems like something you would miss. But maybe not. Let's just say, if I didn't have my glasses, I would notice immediately. But maybe they're reading glasses. All right. Number two, what is magnetic flux? So it's the amount of field going through a loop of wire. So it's the amount of magnetic field going through a loop of wire. So if I have like a series of loops like this, it's how much field goes through. So is it one line of field? Is it two lines of field? Is it three lines of field? How much field goes through? That's called the magnetic flux. Which is where the term flux capacitor comes from Back to the Future. I'm sure all of you were worried about that. And last one, what is electromotive force? So it's also called EMF, which you may have heard of that before. Electromotive force it's a fancy word for induced voltage. Okay, fancy word for induced voltage due to electromagnetic induction. So electromagnetic induction is when a changing magnetic field through a loop of wire induces a voltage. The name for the changing field through a loop of wire is called magnetic flux. And the name of the induced voltage is called EMF. So basically, to simplify it down, it's when a changing magnetic flux induces an EMF. If you want a really short definition, it's when a magnetic flux causes an EMF. That's what electromagnetic induction is. Okay? All right, give me one thing that you think might affect the amount of EMF induced in a wire. Braden. Yes, the number of coils. That is one. And the symbol for that in the equation is N. And the reason the number of coils matter is because more coils gather more magnetic field. So the more coils you have, the more amount of field is going through. They just build on each other. So more coils gather more magnetic field. Because essentially, the first loop gets an induced EMF, the second loop gets an induced EMF, the third loop gets an induced, the fourth loop, they all get an induced EMF, and they just all add up. So the more loops you have, the more EMF you gather overall. Good, so we got the number of coils. We got one down. Give me another one. Speed of the magnet, yes. So I'm going to say the rate at which the field changes. That's what the speed of the magnet is doing. So you have to have a change in the field. And so the rate at which that field changes is the second thing, and that's called T for time, the time it takes to do this. Okay, and this is because a quicker change makes more EMF. So changing the field faster makes more EMF. It's a terrible E. There, EMF. All right, good. We got 2 of the 3 things I thought you would get. What's a third one? So far, so good. What we got, Gabe? Say one more time. So the direction is going to come into effect. That doesn't affect how much. Like if I put the south end versus the north end, that'll change the direction. It won't change how much. But you're exactly right. We're going to get to the direction in a little bit. So you're not wrong. You're just not right. Yeah.
The strength of the magnetic field.
So how strong the magnet is. Now this is one that you couldn't really test, but you kind of saw it in a roundabout way. So if I put the magnet through, that's like the strongest the magnet can be. If I put the magnet next to it, the magnet's a little weaker, and so it doesn't have as strong of an effect. So the third thing is going to be, the strength of the field. How do I want to phrase that? The strength of the field kind of goes in with... Oh, yeah, we haven't put that one in yet. No, yeah. So the strength of the changing field. Forgot we hadn't done that one yet. And that is going to be delta B. Remember, B is magnetic field. The reason it's delta B is because it's a changing field. It's not just a field by itself. It's got to change. Has to change. So that's why it's delta B. Okay. There's one more left. But it's not something that was tested in the lab. I want to see if you can guess what it is. You already guessed, Gabe. I'll come to you if no one else guesses. Any guesses on what else it might be? I'll give you a hint. It's something to do with the coils.
Is it like the thickness of it?
The size. So like how thick they are, what shape they are, how big they are. The size of the coils is the third thing. The third thing. Good job, me counting. Fourth thing. The size of the coils. And that is A for area. And I forgot to mention about the strength. So stronger fields make more magnetic flux. So the stronger the field is, the more flux there will be. And again, flux is how much field is going through the coils of wire. So the stronger the magnet, the more field there will be. Okay? And for the size of the coils, bigger coils will contain more field. And thicker coils will conduct the current better, and just the coils themselves will have an effect. Nice. Look at you guys. So smart. Okay, so let's look at the equation. So this is called Faraday's law. We already did the explanation for the different parts. So there's 4 parts in it. There's actually a 5th, which we'll get to in a second. And it's this, EMF. So the induced motive force, the induced voltage, is equal to... Gonna hang you in suspense. Negative. Don't worry about the negative for now. Just, it's negative. NA delta B over T. The negative is due to the direction. Remember I said direction was going to be something that mattered, and when you looked at the lab, you saw there was some stuff going on with direction. So the direction matters. That's why the negative's there. We'll get to that a little bit later. But that's the equation. Negative NA delta B over T. Not that bad to plug in. You'll have to figure out what the change in the magnetic field is. I'll give you these other things, and then you solve for EMF. Or you may know what the EMF is, and you have to solve for the other things. So pretty straightforward. And none of these variables are particularly weird. N is literally just a number. T is just the time. Delta B is a field, a magnetic field, just how much it changes by. And A is an area. That's the one that you'll have to do a little bit work with. Like if it's a circular, you'll have to use pi r squared. If it's a rectangle, you'll have to use length times width. But you'll use the area, and I'll give you those. You don't have to memorize areas. That's silly. Okay, on to the back page. All right. If voltage is induced in the wire, what else must be induced? So if there's a voltage, there must be a current. Not bad. And here's the trickier one. If there's a current, what must there also be? Starts with the M. Magnetic field. If there's a current, there has to be a magnetic field. So what happens is you have this effect where you create a voltage which creates a current which creates a magnetic field. It does some weird stuff. And what we need to figure out is Lenz's law and what that has to do with it. So what is Lenz's law? Well, here it is. Here's Faraday's law. So EMF equals negative NA delta B over T. So that's Faraday's law. Here's Lenz's law. Ready? Whoop. Yeah, Lenz's law is literally the negative sign. So Faraday came up with NA delta B over T, and Lenz was like, it's always opposite. Give me a negative sign. And he got a negative sign, and they called it Lenz's law. It's like the greatest piggybacking of all time in science. He's just like, oh, yeah, it's negative. And they're like, whoa! And they gave him his own thing. It's amazing. One of these days, I, too, hope to piggyback on someone else's famous idea and get my name in it. The Borcherding corollary, which is like there's this super huge, complicated thing, and the Borcherding corollary is like, it's negative. And everyone's like, whoa!
Actually, there's supposed to be a theory in here.
That's right. It's squared. Oh, mind blown. So this is Lenz's law. It's the negative sign. And what it means is that it's always in the opposite direction. So the induced EMF / magnetic field are always opposite the direction you're doing.